scientific description evolve over time? If so, have they improved or regressed? Welcome to GeoCave! I'm Asha, I'm a geologist from Norway, and on this channel we delve into all things geology. Yet, isn't it true that all science are fundamentally linked to geology? Yeah. Well, I've previously discussed paleomagnetism, which is actually one of my most popular topics here on YouTube. Surprisingly, I realized that I hadn't covered the basic terms. So many years ago, I acquired an old encyclopedia from the early 20th century, and it has been a treasured resource ever since. Today we will be exploring magnetism concepts from this Danish written gem. I have translated it as accurately as I possibly could, and I have categorized it into vectors and scalars. So stay tuned for next week's video on scalars. Pour yourself a comforting cup of your favorite beverage, and let's see what's in the cave today! So today's themes are the vectors, and we have a magnetic force, magnetic field, and magnetic moment, and magnetic intensity. So if you hang a bar-shaped steel magnet on a thread so it can spin freely in the horizontal plane, it will align itself with the Earth's magnetic field, pointing north-south. The end of the magnet that points towards the geographical north is called the north-seeking pole, and the end pointing towards the geographical south is called the south-seeking pole. So when you bring another magnet close, you will notice that like poles, north-north or south-south, repel each other, while opposite poles, north-south, attract each other. This magnetic force between the poles follows Coulomb's law. And it's directly proportional to the product of the magnetic pole strength, and inversely proportional to the square of the distance between them. The simpler term, the closer and stronger the poles are, the stronger the force. But as they move apart, this force quickly decreases. So, yeah, we have it like this. M1, M2, and our distance. Yeah, that's Coulomb's law, the old-fashioned way at least. The magnetic field is very simple. It has a very simple description, and it's just everywhere in the room around a magnet a force will work. This room force is called the magnetic field. Yeah, and so let's jump to the third one. Magnetic moment. Again, if you have in a steel magnet shaped like a rod, the magnetic poles are not just at the very ends, but can be found within the material near the ends. So imagine a straight line running through the magnet from one pole to the other. This is known as the magnetic axis. The magnetic moment is a measure of the magnet strength and direction. It's calculated by taking the amount of magnetic charge in one pole and multiplying it by the distance between the poles along the magnetic axis. So the magnetic moment tells you how strong the magnet is and which way it points. I think it has something like M times L. No, I wrote it the wrong place. Like here, M times L. That's like the old-fashioned value of it. Okay, last but not least, magnetic intensity is a way to describe how much the magnetic charge or strength there is in a certain area of a magnet. So imagine you have a flat plate that is perpendicular to the direction of the magnetic field, and you're looking at just 1 square centimeter of this plate. The magnetic intensity tells you how much magnetic force is packed into this small area. As the external magnetic force increases, so does the magnetic intensity, but only up to a certain point. After it reaches its maximum value, it won't get any higher, no matter how much more you increase the magnetic force around it. It's like filling a cup with water. Once it's full, adding more water won't make it hold any more. Yeah, and that's a glimpse into the vectors of magnetism through the lens of a 19th century book. You might have noticed that back then they used physical descriptions as definitions. Next week we will unravel the mysteries of scalars. So thank you for tuning in. Stay curious, keep exploring, and have a rocky day!